Hi everyone. Going to do our reflections again, and there'll be some specific videos to go with this, but I thought I would try and answer qualitatively, maybe draw a few examples of things that might be helpful. So let's go. Let's see. So if I skip over some things, it's because they've been repeated. Um, Very first thing, the concept of dot product and work. So this is a really great question. The the idea behind the dot product, as Professor Stone King pointed out, is that it helps isolate the only component of the force that is in the direction or the opposite of the direction of the path you're traveling. So you might have a path, say you're going from A to B. And yet, you're doing this in the presence of some force. Okay. Let's say that this is a hill and you're doing this in the presence of gravitational force, which would point, say, down like this everywhere, and it would be constant. I haven't really drawn it constant, but bear with me. Say it'll apply. Um, as you travel along this path, say this is you're walking up a hill, right? Um, at any point, the direction vector, your dr, for example, is tangent to that surface. You're walking along, just if you think about, you take one step up a hill, you might draw your vector, your change in direction like that purple arrow. And then at this point, it might look like that. And at this point, it might look like that. And at this point, it's kind of straight across, and this point is starting to go up again a little bit, exaggerating a little bit. Why is this important? Well, the path you're taking, the things in purple are we'll call it delta R, but we could also call it R or dr, or we could call it delta X, right? So these are the small increments in paths that you're taking. The green arrows represent the force, right? So that shows where force is being directed. And if you look at that, that seems like it's quite complicated when we're trying to find out how much effort, how much work are you going to expend along this path? Well, if you are moving perpendicular to the work, to the force, it doesn't really cost you anything, right? Think about the situation that looks like this. You're moving like this, and the force points like this, both at the beginning of your journey and at the end of your journey. Well, there's no real difference, right? You don't feel, for example, heavier as you move from A to B. Um, so it's the same difference if you're here as if you're here as if you're here. You could slide along that surface and it wouldn't take you any effort, right? And so the dot product in the description for work. So if we look at the most general thing, we could do an integral, but let's look at f dot dr, and we are integrating along the entire path. Why do we take that cross product? Well, the dot product picks out only the piece of the force that points in the direction of your path. Right? So for every one of these pairs, we have an angle theta. Okay. And sometimes what we say with this is that we want the projection of the force on our path or the projection of the path on our force. So either way, it comes out to be the same thing. And if you look at your path, you can see if you look at, say, this first one, part of it is going straight out. Well, that doesn't cost you anything to go that distance, but then part of it is going up. right? And all we really care about is the part of the path that is either parallel, points in the same direction, or anti-parallel. So again, we could look at this path and just that segment of it is pointing along the direction here, just that tiny section. By the time we get to here, none of it, the path is perpendicular to the force. By the time we get up to here, right, it's, again, it kind of, there's a little bit of repetition here because we're going more than 90 degrees, but it's the same thing in terms of only picking out the piece of your journey that is in the same direction of the force or in the opposite direction. Now, if it's in the same direction of the force, it means that something is pushing you while you're walking, which means you're going to speed up. You're going to accelerate. If it's in the opposite direction that you're walking, then you're walking into a headwind. It's pushing against you. So you're going to slow down. So the way that we describe this then again is for, let's say it's a constant force like I've drawn here. It would be F dot dr, which is the same thing as F times delta R times cosine of that angle theta, which picks out just the piece that points in the direction of the force, right? The direction that's perpendicular to the force doesn't really do anything to your journey, right? The gravitational force isn't pushing you sideways, right? And it's not pushing you backwards, it's pushing you down. So the only time you have to expend work is when you walk up. And the only time you get negative or where you get positive work is when you go down. You speed up when you're falling down, you slow down when you're walking up. This is related to the work energy theorem. So this was the last thing that we did. So the work energy theorem, right, is that the net work done, so W net, is equal to the change in kinetic energy, the energy that's associated with motion. That's 1/2 mv final squared minus 1/2 mv initial squared. Why do we care about this? Well, if we do positive work on something, that is, we give it a push in the direction that it was originally traveling, then the final velocity will be bigger than the initial velocity. Right? The change in kinetic energy, the energy that's associated with motion, will increase. And if the masses are the same, that's not changing. That means the speed has to increase. Right? So if you move in the direction of a force, you're going to speed up. If you move against that force, you're going to slow down. And the way that you can tell how much that costs you or whether you get something back from that trip is the work energy theorem. If the work done is positive, you're going to speed up. If it's negative, you're braking, you're going to slow down. In order to answer all of those things, we need to use the dot product because even though work and energy, by extension, uh, are scalars, that is, they only have magnitudes and they don't have directions, they are computed from the fact that you have a force vector, and a path vector. And the question really is, are you pushing against a force? Are you being pulled by a force? So that dot product pulls out that component. Okay, that helps. Let's see. Okay, need some help with free body diagrams since we're adding so many new concepts and forces. How do you choose which forces to include and exclude in a free body diagram? excellent question. I'm sure that there are many more. No, there are more because I looked at the list ahead of time on what to do with free body diagram. So free body diagram, what are the rules for free body diagram? The very basic rules are that we are going to draw whatever it is. If it's a cow or a spotted cow or a six-pack of spotted cow, we're going to represent it as just a point. We're going to assume that all the mass is concentrated at that point. This is a simplification because most of the problems that we're looking at don't really matter, certainly in this class. The extent of the object doesn't matter as much as the how the center of mass is moving through space. So that's the first thing. Then the second thing is depending on the problem, I mean, it doesn't really depend on the problem. You have to make this choice. You have to choose a coordinate system, right? You have to choose which way is positive x and which way is positive y, and whether those axes are tilted or not, right? Now, this will depend on the kind of problem you're doing. As we saw with the ramp problem or a ramp problem, there are different ways in which we want to orient it. Then the last rule is that you then include, based on this choice of axes, only the forces that are specifically mentioned in the problem and that are individual forces. That is, they're not net forces. So what do I mean by that? I mean things like friction, things like gravity or weight, the normal force, spring force. Those are things that are due to the interaction, either the interaction of a long-range force like gravity, or the interaction of the contact between two surfaces. So in the case of, say, a ramp, let's put this, let's erase this, erase all of this for a second. Let's make our ramp. Everybody loves a ramp problem. I hate ramp. All right, so you got your object here. Let's put an angle theta here. There's always going to be an angle theta. And the question, suppose the question is, draw a free body diagram for this problem. What are the forces in this problem? And let's assume that friction is important. Okay, so always there's going to be weight. So you can put that in. I'll use F sub W. If you have a ramp, there's going to be a contact force that is normal, that is perpendicular to the contact between those two surfaces. And then we have to put in friction. Now, the question about friction is an interesting one because it depends on the problem. If the problem is asking about what's the frictional force that's required to hold this block in place so it doesn't fall down, well, you imagine the block starts moving down a little bit. Friction always opposes motion. So in that case, friction would point up the ramp. On the other hand, if we had a problem, say, where you were pulling something up a ramp, suppose we had this ramp, an object on the ramp, and it was attached to a string across a pulley, and a weight was pulling it across. Well, then we would have the normal force as we did last time. We'd still have the weight. We'd have a pulling force, which is called that FP. And since this is now moving up the ramp, we would draw in a frictional force that points down the ramp. Friction always opposes motion. Okay. Then when it comes to solving these problems, we need to break these up since these are all vectors and say we're trying to solve for the motion, either the acceleration or we're trying to find the force that holds the block in place or what have you. Generally speaking, we like to have our axes, especially for an isolated ramp problem like this, point along the ramp. We can choose to have it the other way. That is, we could draw it like that. And as long as we're consistent, we'll get the right answer. We'll get the same answers. But the idea here is that now we can break up, especially in a case like this, right? If you look closely at this diagram, right, the friction force points entirely in the x direction. The normal force points entirely in the y direction. This is one of the reasons why we would do such a thing. And then if we look at the weight, we can see that there's a component of the weight that points in the negative x direction, and there's a component of the weight that points in the negative y direction. Okay? And then the question would be, if we want to solve for, say, how does this block stay in place, that becomes a statics problem. And we would set the sum of the forces in the x direction to 0 and the sum of the forces in the y direction to 0, and say solve for the friction that's required to keep that block in place. We can see that the friction minus the x component of the weight is the total sum of forces in the x direction, and the normal force minus the component of the weight in the y direction is got to be 0, otherwise the block would go right through the ramp. This, by the way, I know this is another question later on, is why the normal force isn't always equal to the weight of an object. It is at most equal to the weight in most circumstances. It is only equal to the weight when an object is sitting on a flat surface and the weight is the only problem pointing in the y direction. The normal force is the only reason why that block is not sinking through the floor. In this case only, the normal force is equal to mg. Here, that's not true. The normal force is equal to a component of the weight, a fraction of the weight. Okay? All right. And then, of course, it can get quite a bit more complicated if you had a pulling force. But again, if you had your x and y coordinates like this, then the pulling force and the friction force are purely in the x direction. The normal force is purely, or this is x and this is y. And the normal force is in the y direction. There's a component of the weight that points in the negative x direction, and there's a component of the weight that points in the negative y direction. You could use those to solve the problem. So the short version answer to your question about when do we draw these forces is read the question and make note of what specific forces are mentioned. And if there's a contact between two surfaces. If there's contact between two surfaces, then there could be friction, and there's almost certainly, well, there is certainly a normal force. You never have a normal force if you're just out in space. Okay, so for example, in the tetherball problem, and a few people had some problems with this, but if you remember the GPS from Tuesday, you had a tetherball that was going out here and was moving around in a circle. And the first part of this problem was to draw the free body diagram for the tetherball. So the free body diagram for the tetherball, let's say X and Y look like that. There's weight, and then there is tension due to the string, and that's it. Okay, there's no normal force because there's nothing for this ball to be normal to. There's a tension force that pulls it up in that direction, but that's it. Now, there's one other thing in this problem that you never, ever, ever put into a free body diagram, and that is the centripetal force. So if this is moving around in a circle, you would never add, for example, another force and call it the centripetal force. And that's because the centripetal force, or the force that causes uniform circular motion, is a resultant force. It's the combination of all forces that point into the center of the circle. And so your job, whenever you see uniform circular motion, is to find what forces are responsible for that uniform motion. In this case, in the circular direction, in the circular path, it was the x component of the tension. It was the only thing that pointed toward the center of the pole. Okay. Give you another example. This one's relevant to a homework problem. You have a plane that is banking and using that bank to turn. So have you ever wondered why you turn in a plane when you bank? Huh. Well, if we think about a plane that's just flying at level, and here, let me draw the picture first and then the free body diagram. So here's the fuselage of the plane. That's the tail, and then those are the wings. Okay, and it's moving out towards you. If we were to collapse this to a free body diagram, ignoring wind resistance, we would have weight, and then holding us up in the air is a lift force. Now, that lift force is something we're going to talk about actually in the section on fluids, interestingly enough. As a plane moves through the air, the shape of its wings are such that the top side of the wings are a little bit bigger than the underside of the wings. And as a result, the air flows faster over the top of the wings than the bottom of the wings. And because the air flows faster, the pressure is lower on the top of the wing than the bottom of the wing, and that gives you lift. So the next time you're flying, remember, you're only up in the air in a tin can because the wind across the wing is going just a little bit faster than the wind under the wing. Ta-da! All right, so this is level flight. What happens when a plane banks, that is, turns at an angle? Well, let's draw the picture first, because the interesting thing about the lift force is that it is perpendicular to the wings. So you need to kind of draw the plane in and then add the free body diagram. Again, this is for one of the problems in the homework. So you have the weight as usual, and then you have a lift force. And that's it. But if you look at this, and let's say for fun and giggles here, we put in our axes so that x points off in that direction, y points up. Well, the lift force now has a component that points in the x direction and a component that points in the y direction. Suddenly now, this is a combination of a statics problem and a dynamics problem. In the y direction, it's a statics problem, assuming that we're at level flight. The sum of the forces in the y direction is going to be the y component of the lift minus the weight. And that has to be equal to 0. So that allows us to solve for the lift. What happens in the right? Well, if the plane is leaning, if you've ever been on a plane and you know when a plane banks, it starts to turn. And this is one way a plane can execute a very long turn. Another way you can do it is by turning the rudder, and that actually turns the plane in the direction of its flight. But if you bank, that means that there's an x component of the lift that points to the center of a circle. All of a sudden, then, f sub x is now equal to, that's in the positive direction, the x component of the lift. There's nothing else in pointing in the x direction. That has to be equal to the acceleration in the problem, of the force that's causing acceleration. But if it's moving in a circle, that's equal to mv squared over r. So that's how you can solve. There's a particular problem where you're looking at the minimum radius or something like that for a plane to be flying level at a particular speed and a particular angle. Now, your job is to figure out if this is the angle that the wing makes, which one of these angles does that correspond to, right? You need to find, do you use sine or cosine theta to get lift force X or lift force Y? I hope that helps. There's some other examples in the notes, so please look at those. Okay. What else? Incorporate kinematics. Okay, how do we incorporate kinematics into a mechanics problem? I think you mean a dynamics problem. That's a very good question. The one way that we can do that is if the acceleration is constant, then we know, well, we know even if it's not constant, right? We know that Newton's second law, F equals ma, right? So A equals F over m. If the force is constant, the acceleration is constant. If the acceleration is constant, we have a number of equations of kinematic equations of motion for constant acceleration that are at your disposal. Hope that helps. Little confused about the trig and the ramp problems. You're not alone with that. I need a few examples before I understand the mechanism. The idea here, look at the notes where I kind of flip the triangle. The idea is to identify the similar triangle. So if you have a triangle with an angle theta, and you have weight force and the normal force, and we're going to choose because we know that this is a ramp problem and there's no centripetal force, so this is why we would choose this. And that means that if this is the normal force and this is the weight, the reason why something would slide down the ramp is because something is pointing in the negative x direction. So the only thing that could possibly, in this setup, point in the negative x direction is a component of the weight. So we make a right triangle. That's 90 degrees, and that's 90 degrees. And what we're after is F weight x. And how is that related to F weight, the total weight? Okay, so then the question is, which of those angles in this triangle corresponds to the angle that characterizes the ramp? You flip things around, rotate it, expand it, maybe you can see what is the similar triangle and the appropriate angle. You could use some other trigonometric arguments if you extended these things down and use parallel lines. But I think that if you look at this, try and convince yourself, especially in this exaggerated form, that this is a narrow angle here and this is a narrow angle here, right? And so that for almost every ramp problem that we do, that's going to be the case, that the top of that triangle is equal to this bottom angle. And so F weight x is going to be the weight times sine of theta, whereas F weight y is equal to the weight times cosine theta. Okay, which is kind of different from what we're used to using when we decompose things into x and y. But to freeze this and really commit this to memory, also look in the notes, because we really do want you to try and get some work practicing that, because it is really confusing. It confused me the first time I did this. Okay, I hope that helps. Why is Fn equal to Fw sometimes? Okay, I think I explained that it's only equal to it when all of the normal force is due to that weight, that it's a Newton's third law reaction pair. If there's a ramp, then the normal force, which is perpendicular to that interface, that surface, then only a small part of that force of the weight can point in a direction normal to that ramp. Okay, again, just remember that normal means perpendicular to. Okay, let's see. Circular motion regards to force and the idea portion of this quiz today. So circular motion. Circular motion, what you need to remember about circular motion is that whenever you see something executing uniform circular motion, that means that it's moving at a constant speed around a constant radius, and that the magnitude of that force is mv squared over r. And it points towards the center of the circle. At every point, something is trying to go in a straight line, and every point is being bent towards the center. And then the other thing to remember is that you never ever include it in a free body diagram. Okay. All right. Let's see. How can Superman fly at nearly the speed of light? Well, he can't. Um, take science as superheroes, and I'll tell you why. Centripetal force and normal force when there is no incline. Okay, so um, in the example that we did, so that in that case, I mean, there you may be referring to the quiz, or you may be referring to the last example I did in lecture on Tuesday. But let's assume that it's the car. So F sub n, and you have F weight, and then you have a frictional force, right, which points to the middle of a circle. Okay. Now, the centripetal force is due entirely to the frictional force, and that's because in what you're basically looking at is you're looking at a car coming towards you trying to execute a turn. And you know, because you've been in cars that have gone on turns too quickly, that the natural inclination of a car that's moving too fast for a turn is to move outward. If it's moving outward, friction opposes that motion, so it'll point towards the center of the circle. And since this is the only thing that points in the center of the circle, that's going to be the only thing ultimately that is responsible for the centripetal force. Okay. I hope that helps. So the ramp problems that have centripetal force, in that case, you're looking for some other mechanism to hold something up. And you have a very interesting but kind of tricky, it's involved problem. It's the last problem in the homework where you have a car going on a ramp and there's friction. So there is a bit of friction and there's a bit of the normal force that's responsible for the centripetal force. Anything, the sum total of anything that points to the center of a circle can be responsible or is responsible for uniform circular motion. This is work energy. How to solve for kinetic energy specifically? 1/2 mv squared. Okay. Definition of kinetic energy is the energy of motions, the energy that is imparted by something when it strikes you, if it has a particular mass and a particular speed. 1/2 mv squared. We didn't go over the derivation of that. That's a little bit beyond this course. It is in the textbook if you want to look at it. It takes a little bit of calculus, but it's not horrendous. But it's just not particularly important for the purposes of this class. Definition of friction and other properties of friction. Okay, so friction arises because of essentially imperfections in the surface. If you were to zoom in, basically, between my delicate hands and look at the surfaces, right? They're not completely smooth. If they were utterly smooth, it would just slide right across each other. But they're not. There's little ridges, like your fingerprints, which actually give us the ability to stick on things. That's friction. That's a kind of friction. And it's this surface irregularities that you push against and that you have to overcome because those irregularities can kind of interlock with each other and you have to kind of break them and move them along in order to get going and then keep going. And in fact, you know from regular experience, if you push something, right, push something, it'll eventually stop. And that's because of friction, because you're moving across this surface and that interaction is providing a force in the opposite direction. Now, to continue moving, you have to continue applying a force. You have to have a force that points in the opposite direction. And in fact, if you have a force that is exactly equal to the frictional force, you will move at constant speed. You won't accelerate. Your net acceleration will be zero, but that doesn't mean you don't move. This is a really, really important point from the last couple of weeks. Namely, if F net is equal to zero, so the net force, you sum up all the forces in particular directions, suppose that's zero. That does not mean necessarily that you're standing still. All it means is that your velocity isn't changing. If your velocity is zero, then it's going to stay zero. If you're moving at a constant speed, you'll be at a speed, say 60 miles an hour, and the net force is zero, then you're going to continue moving at 60 miles an hour. Here's a good example of this. You know in real life that there's friction between the wheels of a car and the road. Right? If you want to maintain constant speed, right, you have to keep your foot on the accelerator, right? The pedal that supplies power to the wheels, that keeps the wheels moving with some acceleration that is a constant forward force. That forward force exactly cancels out when you're moving at constant speed at, say, 60 miles an hour, the friction from the wheels on the road. And so you can then travel at 60 miles an hour. The moment you let your foot off the gas, off the accelerator, what happens? You start slowing down. If you're going really fast, that might take a while because the frictional force isn't particularly strong necessarily. If you're going very slow, you come to a stop pretty quickly, right? So if you're moving at constant speed in a car, that's because you're applying a forward force that is exactly the opposite of the frictional force. That was a good question. Okay. Did that on scalar products, work energy theorem. We will talk about energy conservation next week. Okay. I already discussed scalar product. There's also a video on scalar product on the website. Some more work on springs. We'll return to that on Tuesday. Um, the main thing to remember about springs is that springs and Hooke's law, for example, are restoring forces. They're forces that act linearly. That is, you pull a spring apart twice as big, you get twice the amount of force, and in the opposite direction of the extension. So if you pull out, the force points in. If you squish in, the force points out. That's why F is equal to minus K dot delta, or K delta X. It tries to restore the spring to its original unstretched length. And the neat thing about springs and the spring force, the reason why you're learning about it now, is that almost everything in the world behaves at some level like a spring. From the molecules in your body, DNA. For example, you can pull apart DNA and you can actually, and I think you have a problem in the homework about this, you can calculate an effective spring constant by how stretchy something is. And so many things in this wonderful universe that we live in behave like springs. That is, they try and reestablish their equilibrium by applying a force that points towards their original configuration. We'll do more of that on Tuesday. Next week, we will talk about conservation of energy on Tuesday, and then Thursday, one of my favorite topics, collisions, and how that is another expression of Newton's third law, which is conservation of momentum. Momentum is where it's really at. Momentum is really the mathematical definition of motion. So anyway, I hope that this is all helpful. Please watch these videos. If you have any questions, remember that I have open hours from noon to 4. Holy shit. I would go to those if I were you. Um, and otherwise, have a great weekend. You guys are doing great. 3 weeks down. Don't forget the 3-week survey is just about open. Should be open right now. So go fill that out. Yeah. Okay. Have a great weekend. See you Tuesday, maybe Monday, hopefully Monday. All right. Bye-bye.